All right, so I've been explaining that starting from second order differential equation, because trying to solve it in an honest fashion often takes too long, we'll be using some guesswork, some educated guesswork to guess the answer, and that will be justified because mathematicians did all this work for us, which was the existence of solutions and uniqueness of solutions. These are some mathematical theorems which are very hard to prove, so we will just have to accept it. Okay. All right. So let's see how this thing is done. Okay. So let's say y double prime is equal to y. How would we solve this? I mean, I know one function whose derivative is same as itself. What's that?
e to the x.
E to the x. So this definitely is going to satisfy this, because even if you differentiate this twice, it's still going to be the same as before. Now, can you think of another function that will satisfy this? Cosine will be negative, right? If you differentiate cosine twice, so it will be negative of cosine.
Sine.
Sine is the same story.
0.
Oh, 0 is useless. I mean, 0 is a solution here, but it's not going to give us something to play with. I mean, basically, what are we trying to do? We want to guess two completely different solutions, and if I have one solution and another solution, I want to say, in general, the solution is C1 times the first function plus C2 times the second function. That's what we're trying to do, right? So we want a function that's not going to go away when we try to multiply C2. But C2 times 0 gives you 0, so that's not going to help us. Any other?
C times e to the x.
Okay, well, C times e to the x, that we already, the moment we write this, we know that C times e to the x is a solution. C1 times e to the x will be one part of the solution. We need plus C2 times another function. What could be the other function?
e to the 2x.
Okay, that's another good try. E to the 2x, if you differentiate twice, you get what? 4 e to the 2x. So that doesn't work. But that a good direction, okay? Just keep those suggestions coming. Yes?
What about 1 over y?
Huh?
1 over y?
1 over y?
Yeah.
No, I'm asking you for what y is equal to.
Oh.
Y has to be a function of x. Okay, you can't say 1 over y. Yes.
Is it tan x or secant x?
Tan x differentiated twice will give you something horrible. Tan differentiated with secant squared differentiated will be even worse. And same with the secant. It will just get worse. Yes?
ln x?
ln x differentiated twice. If you differentiate once, it's 1 over x. Differentiating one more time, it's negative 1 over x squared. So that doesn't work either. You know, for polynomials, the orders go down, right? For most of the other functions, when you differentiate, it just gets worse and worse. So really, those that stay in a similar form is e to the something. So you should think about it in that direction. E to the what? When you differentiate twice, or is it the same as before?
The negative x.
That's good. Let's try that. If you have e to the negative x, y prime is negative e to the negative x. If you differentiate again, you get negative of negative e to the negative x, which is e to the negative x, which is same as the original. So e to the negative x is a solution. Okay? And now you can say in general, the solution is y equals to c1 times e to the x plus c2 times e to the x. That's our plan, okay? Let's try another one. What if you had y double prime equals to negative 1?
Cosine?
Hmm?
Cosine?
Yeah. That's a solution. Differentiating twice gives you negative cosine. Do you know another one? Sine. Sine is the other one. So in general, you know that this is y equals to c1 cosine x plus c2 sin x. Okay. So our plan is to find individual functions that satisfy it, and then you just take linear combinations. Sometimes this is called the superposition of two functions. Physicists like to call it superposition. Mathematicians like to call it linear combination. Now, let me give you something else to think about. What's e to the ix double prime? What's that? If you differentiate once, you get what? What's the first derivative? What do you get if you differentiate this place? I e to the ix, right? That's the first derivative, so you have to differentiate one more time. So what do you get?
Squared.
I squared e to the ix. What's I squared?
Negative 1.
Negative 1. So you get. So what? What does this tell us?
That can work for the same.
That this means that y equals to e to the ix can work for this equation too. Right? Okay, then things get interesting. Why is it interesting? Well, we know that by the uniqueness property of differential equations that since this second order, then it will, providing two initial conditions will give you a unique answer. That means any solution that has two free variables, C1 and C2, should give you all the solutions. So basically, the implication of the uniqueness goes like this. Second order differential equation should have two free variables. That's what it means, okay? First order equation should have one free variable. These are called parameters, by the way. So this is two parameters for two second order. First order equation should have one free parameter. A third order differential equation should have three parameters, and so on and so on. But once you accept that this is another solution, and you write it as, okay, so now I have three functions, so is this another way to write down the general solution? Then you know that something's wrong here. It doesn't look right because now you have a second order differential equation having three free parameters. So something's not going right. Okay? So this is the time when you start thinking about can one of my solutions, is one of my solutions actually other solutions in disguise? Which in this case is true. Okay? So then we come up with the problem of linear independence. So let me talk about the problem of linear independence. Problem of linear independence. So the thing that goes wrong here is the following identity. E to the ix is cosine x plus, let's see if anyone remembers. E to the ix is cosine x plus I sine x. What is this called? Don't remember?
Property, right?
It's called Euler identity. Euler identity. Okay. I thought you deal with this in electrical engineering course, E290, right?
Just starting more.
Oh, you're not taking it. I see. Okay. All right. So this is Euler identity. And look at what's going on here. This is like 1 times cosine x, which is already here. I times sine x, which is already here. So it's actually the following. We wrote this, and the moment we wrote this, we were saying, hey, this is a new solution, right? So we just put it as a new solution, plus C3 times u the ix, okay? But later we found out that no, it's not a new solution because it's representable by the 2 functions that we've already found. See, in fact, if I set C1 to be 1 and C2 to be I, it is this solution, so this solution is included in here. It's nothing new. You see what's wrong with saying this is a new solution? Setting this as a new solution completely misleads people because this is not something that cannot be expressed by this. So the question is e to the ix expressible or not as a linear combinations of other 2 functions? And the answer is no. In this case, the mathematical word that we use is the following. We say e to the ix is not linearly independent from cosine x and sine x. And that's the trade-off. That's the small price to pay when you're trying to solve by guesswork. See, the small price to pay is that whenever you make guesses about, oh, we found this as a new solution, that is a new solution. Oh, here's another one. And you have many different solutions and you try to come up with linear combinations. The question always that you have to ask is, are they linearly independent? If not, then you have to come up with the smallest set of linearly independent ones so that you really get genuinely new functions, and then you're going to take the linear combinations of them. That's what you have to do. Okay? That's the small price to pay when you're trying to do the guesswork rather than solving. Okay. Now let's think about this further. Definition. Number 1, functions fx and gx are called linearly dependent if C1 fx plus C2 gx equal to 0 for some C1 C2 not both 0. So let's think about what this means. Suppose we are given 2 functions. So think like this. I found a solution. oh, it's e to the x. And some other person says, oh, I found another one. It's 2 times e to the x. Okay? And the next question is, okay, can we include both of them, like c1 times this plus c2 times that? And the answer is, can we do that?
Yes.
Okay, all right. Y double prime equals to y. Okay, one guy finds this, another guy finds this. And they say, okay, the general solution to this is y equals to c1 times e to the x plus c2 times 2e to the x. Are we all happy? We're good?
No.
Is that good?
No.
Yes? No?
Yes.
No.
Why not?
C is a constant.
Huh?
C is a constant. So
This is basically saying c1 plus 2c2 e to the x, right? And so you have like, this is just some generic constant. All you're saying is the solution of this is some constant times e to the x. That means you completely missed the other solution. What was the other solution? E to the negative x. This solution can't cover that one. So you've missed half of the solution. That's bad. You see what's going wrong? What's going wrong here? All right. You don't want to say, oh, these two are completely different solutions, so I'm happy to put the linear combinations. That's bad. Okay. We want to say that, oh, okay, I see that you did hard work, but you know what? I think what I found is already including yours. I mean, they're linearly dependent. That's what I want to say. Okay? This is not that hard if you think about it. It's just think about what we're aiming for. We want genuinely new functions. Okay? So we want to devise some words to say, oh, this function is different from that function. That's why I want to say. Okay? All right. So now, why are these two functions linearly dependent? Because one function, say g of x, can be obtained from this function just by multiplying by 2. All right? In other words, here's a situation. Let's say two people found these two functions, and they found out that, oh, f of x is equal to some constant times g of x. Is that good or not? Huh? No, that's bad. Okay? So that means, oh, this is not something new, so you have to go back and search for some other solution. Okay? That's what you have to do. Okay? So this is what we call linearly dependent. Linearly dependent. Bad. Okay? Linearly dependent means bad. Okay? You have to work harder. Okay? To find independent solutions. Okay? Okay? So you could define linearly dependent this way. But a lot of times if you open up the textbooks, rather than putting it this way, they write it in a more symmetric form. This kind of seems to treat fx as something more special than p of x or vice versa. It's not symmetric, right? So people, instead of writing it this way, they just move this to the other side and you get f of x minus cgx. Right? And then you can just multiply another c tilde both sides. And then define this as C1, and define this C tilde times C with minus that as C2. Then it becomes this one, okay? So all this is saying that if the two functions are multiple of the other, that means they're linearly dependent. That's what this means. Does this make sense? Okay.
And you don't want that.
You don't want that. Linearly dependent is bad. You want linear independence. Okay? All right. All right. Number 2. Functions fx, gx, and hx are called linearly dependent if c1 times fx, c2 times gx, plus C3 times h of x is equal to 0 for some C1, C2, and C3, not all 0. Yeah, this condition, it should be there because, I mean, if you don't put that, then you can, it means that you can always put 0, 0, 0. That makes it all three functions, in any case, always linearly dependent, but that's not what we want. Okay? We should have at least one of them non-zero. Okay? And it's the same story. I mean, in practical situations, we say e to the ix is linearly dependent with cosine x and sine x because you can put 1 here and you can put I here, and so it's like C1 times the first function, so it looks like this. So the situation is like this. The third function is some constant times the first function plus the sum constant times the second function. If this happens, is that good or bad? I think you still don't get it.
It's bad.
It's bad, right? It's bad because this is nothing new. It's dependent on the other one. You want to say that this is bad, okay? So h of x is this. See, this is the thing that we want to say linearly dependent, okay? And again, rather than defining it this way, this definition moves the hx to the other side, so it's minus hx, and put 0 here when you move it, right? And then calling this as -1 as C3, and then that could be one example where it's linearly dependent. Sorry. So that's how linearly dependent is defined. And if it's not linearly dependent, then we call it linearly independent. Does it make sense? Okay. All right. So we define what linearly dependent means, but the opposite of being linearly dependent is linearly independent, which is the good thing. Right? Okay. Now let's see if you can actually determine whether two given functions are linearly dependent or not. Okay. So example 1. Show sine x and cosine x are linearly independent. We can do this in two different ways. We can just write this down and show that there's no other way but having C1 and C2 to be 0. Another way is to show that if we say one is the multiple of other, then it fails. I'll go with the other one. Although I define it like this, I'll use that unsymmetric form. Okay. So solution. Suppose sine x is some constant times cosine x. Suppose they are linearly independent. So I should suppose. I mean, this is already ridiculous. We know that sine x is not multiple of cosine x, right? Are we sure? Maybe we didn't know it so far, and it may turn out that this is true. Would you believe me if I said that sine x is multiple of cosine x? Yeah. All right. I almost know that this is not true, but let's try to solve this. Okay? Suppose this is true. And what I'm saying here is I'm talking about an identity for all values of x. When I say this, see when I write these equations, these have to be true for all values of x. It's an equation of functions. Okay. All right. So then I can divide both sides by cosine x. Okay. Then what do you get? Sine x over cosine x is c. We have a name for this, right? What is this? Tangent x. Now what's wrong with this? What are we trying to say? What does this equation imply? That for all values of x, tangent of x is always equal to some constant. That's what this is saying, right? Is that right?
No.
No. Tangent is not a constant function. It never was, right? So since tangent x is not a constant function, this is a contradiction. And if it's a contradiction, where could it have been going wrong? Our original supposition says this is proof by contradiction. If we assume that they are linearly dependent, we come to this contradiction. Therefore, these are linearly dependent. And this actually has some value. I mean, this proof immediately says that when we are approaching this differential equation by saying, oh, we have cosine x and sine x, those are the two solutions, and we write down C1 and C2, we can have peace of mind because I just proved that cosine and sine are linearly independent, right? So these are genuinely two different functions. So I really do have two free parameters, right? And if I have two free parameters for second order, that means I found all possible solutions by the mathematician's theorems of existence and vagueness. So that's how all this fits together. Okay. So there's the value in knowing whether given functions are linearly independent or dependent. All good?